Hashy starts with a tiny database and a simple promise. Give me a record ID and I will find the record. The first version is almost too easy. Put every record on a shelf, one after another, and when a request comes in, walk down the shelf until the ID matches. For a few records, this feels fine. Hashy checks the first card, then the next card, then the next one. But as the shelf grows, the problem changes. The database is not failing to store records. It is failing to find one record quickly. Hashy does not need a faster walk. Hashy needs a way to turn an ID into a location. So Hashy builds the next version around slots. If the database has numbered slots, then lookup can become a jump instead of a scan. But there is a missing rule. A record ID like 1, 2, 3, 4, 5, 6, 7, 8, 9 is not already a slot number. It has to be transformed. One teaching-friendly method is digit folding. Split the key into chunks, fold those chunks together by adding them, and get a smaller number that used more of the original key. Then, modulo squeezes that number into the current table size. If the table has 10 slots, modulo 10 gives a slot from 0 to 9. The exact folding method is not the main point. The point is the shape of the idea. Hashy is turning a large key space into a small table range. Now Hashy has a mapping rule. A key becomes a first place to try. For a moment, this feels like the whole answer. Hashy folds the key, applies modulo, and the record snaps into its slot. Then the second record arrives. It has a different ID, so it is definitely a different record. But after folding in modulo, it asks for the same slot. Oh, that is the first collision. This is not the table being unlucky in some weird exceptional case. The world of possible keys is much larger than the number of slots in the table. Different keys can land on the same starting position. A better hash method can improve distribution, but it cannot make collisions impossible. So the first rule gave Hashy a home slot. Now Hashy needs a second rule for what to do when home is already occupied. Hashy chooses the simplest collision rule first. If the home slot is full, try the next slot. If that one is full too, try the next one after that. Keep walking forward until an empty slot appears, and if the walk reaches the end of the table, wrap around the beginning. That is linear probing. The probe sequence is deterministic. It is not Hashy wandering around looking for a nice empty space. It is the same formula every time. Ohm plus 0, ohm plus 1, ohm plus 2, all modulo the table size. That consistency matters because the table will need to make the same walk later. For insertion, the payoff is immediate. The colliding record still gets stored, and the rule is easy to explain. But notice what changed. The record no longer lives at the first slot its key chose. It lives somewhere along the path. That means lookup has inherited the same path. Now a lookup request comes back for the displaced record. Hashy recomputes the home slot, but the record is not there. That does not mean the record is missing. During insertion, the home slot was occupied, so the record was pushed forward. Search has to replay the same probe sequence that insertion used. Check the home slot. Compare the key. If it is not the requested key, move to the next slot. Compare again. Keep going until the matching key appears. The stopping rule is just as important. If search reaches a truly empty slot, then the record could not have been inserted beyond that point using this probe sequence. So empty means stop. That rule works, but it makes the next operation more dangerous than it looks. Deletion is a trap. Suppose Hashy removes a record from the middle of a probe path. The tempting move is to clear the slot and mark it empty. But now search sees that empty slot and believes the path is over. A later record, which was displaced beyond that point, becomes invisible. The table still contains the record, but the search rule can no longer reach it. This is the moment where the meaning of empty becomes important. Empty does not just mean there is no record here. During search, empty means no record on this probe path was ever placed beyond here. So Hashy needs a third kind of slot state. Not occupied, not truly empty, but deleted. That marker is called a tombstone. A tombstone says the old record is gone, but the probe path continues. Now search can walk through it and find later records. This preserves correctness. But it also leaves debris in the table. Tombstones are not free. At this point, Hashy's table follows the rules. It can map keys, it can handle collisions, it can search displaced records, it can delete without breaking the path. But correctness is not the same as speed. As more slots become occupied, and as tombstones accumulate, the empty spaces become harder to find. This pressure is usually summarized by load factor, the fraction of the table that is in use. For open addressing, the practical pressure also includes tombstones, because search and insertion still have to walk over them. Linear probing creates neighborhoods of filled slots. Those neighborhoods are primary clusters. When a new key lands anywhere inside or near a cluster, it has to walk through the cluster and often extends it. That means the cluster attracts more displaced records. This is why the slowdown can feel gradual. Hashy is still doing the right algorithm, but each operation is walking farther than before. The table did not suddenly break. The paths got longer, and that is enough to make it slow. This is where Hashy grows up from a slot picker into a hash table designer. The mature structure is not one trick. It is an agreement between several rules. First, choose a storage layout, usually an array of slots or buckets. Second, map the key into an initial position. Third, decide what happens when that position is occupied. Fourth, make search follow the same logic as insertion. Fifth, make deletion preserve the paths search depends on. And finally, maintain the table before those paths become too long. Resizing is one answer. Build a larger table and remap the records so the crowded neighborhoods break apart. Notice that resizing is not just stretching the picture. The table size changes, so the modulo result can change too. Records have to be placed again under the new table size. Other collision strategies answer the same pressure differently. Chaining keeps multiple records at a bucket. Quadratic probing changes the jump pattern so the walk spreads out differently. Double hashing uses a second hash to choose the step size. None of these choices makes load factor irrelevant. They just move the trade-offs around. The details differ, but the promise is the same. A hash table stays fast only when mapping, collisions, deletion, and maintenance are designed together. There is one more thing to notice before we close. We did not go deep into every folding technique, and we only gave a quick glimpse of chaining, quadratic probing, and double hashing. That was deliberate. This episode was about the mental model. A hash table is a set of agreements that keep records findable. In the next part, we can slow down inside those choices. We can compare folding methods, look at why different collision strategies behave differently, and ask when each one is worth using. Hashy has learned the map. Next, Hashy learns the roads.